All right, let's get started for today. I see Roshan raising hand. Roshan, do you have any particular doubts?
No, sir. Particular doubts. No,
Yeah,
no
you
one.
raised your hand, right? Okay. All
Yes,
right.
sir.
No
Okay,
problem.
sir.
No problem. Maybe my by mistake. Okay. All right. So, welcome back to this live sessions. This is week three. Um, I hope you all got the YouTube recordings, YouTube videos. So I uploaded all the recording of these sessions, both the sessions, previous two sessions. I uploaded in the YouTube. So you can get it by going to your NPTEL portal, and there will be a problem solving session option or a tab where you can click it and you can open a Google Sheets, and Google Sheet will give you the links of both the sessions. Okay, and it will also have a drive link which contains problems and solution which we discussed in the sessions. Okay, all right. Um, so I'm going to repeat again. Um, if you have any questions for in week one, week two, or previous assignments, uh, please let me know. We can discuss that first, and then I will start solving few problems in this session, so that it will be helpful for you to uh, solve week four assignments. Okay. So before going into week four assignments, do you have any doubts regarding maybe lectures or uh, you know doubts regarding the previous week solutions, assignments, whatever? Okay, please let me know. I will wait for 5 minutes. So if you have any questions, you can ask me now. I have 7 students here. Is there any confusion with the previous week assignments, week three assignments? I see a lot of discussion in the common forum. So, is everything fine? Week three, week two. All right. So, if there are no questions, maybe I will start today's session. So, can anyone tell what we did in the last sessions? Where was anyone attended in the last session? This is supposed to be interactive. You can always switch on your mic and camera, and you can talk to me. You can stop me anytime. So, uh, can anyone of you quickly brief me? What happened?
In last session, we have discussed about rocket stages, propellant mass of the earliest structure,
Right. Thank you, Yogesh.
SSLV.
Mm-hmm. Okay.
We discussed about SSLV,
Mm-hmm.
D4.
Mm-hmm. Mm-hmm. Right. Okay. So, as Yogesh said, we discussed about stages of rocket. The main goal is to place a certain payload at a certain altitude. So, for that, how do you design a rocket? That is the main goal of last sessions. Uh, so that is how the course also progresses. So let's say if you want to study rocket propulsions, what happens is initially you will see why you need a rocket, why you need to uh, put a payload in the certain orbit. And to understanding that, having understood that, what you will do is you will try to uh, find what it takes to put a payload at a certain orbit. So once you understand, so that is what delta V calculations, that's what we did first. So what we need is we need to put a payload at certain height. For that, how much velocity difference we need. That was the first calculations we did as per the course. And then to put this payload at the orbit, how do we do it? What is the means of doing it is through rocket. So we will launch a rocket from the ground, and we will give delta V to the payload using that rocket. So how does a rocket work? So with a single stage rocket, uh, have you guys calculated a single stage rocket calculations for the last class? Maybe I will come to that later. So we can do it either in single stage or multi stage. So so what we saw is we did a multi stage rocket calculations. So it takes we need three stages to put a payload at the orbit. Now, once you understand how many stages you need and what is the thrust you need at each and every stage, you need to know how are you going to get the thrust. So first you understood that what is the delta V you need to to put a payload in the orbit. Second is how are you going to do it? How many stages of rocket you are going to do it? Once you understand the stages of rocket and what are the thrust you are going to uh, you have to give, now you want to calculate. Now you want to find how are you going to generate that much thrust. Okay, so to generate a thrust, we need to burn a propellant inside this combustion chamber, and we need to accelerate through the nozzle. And at the nozzle exit, we are going to have high velocities, and high velocity is going to generate more thrust. So now we are looking it into uh, thrust generation part. Okay, in fact, inside thrust generation, in the thrust generation part, what we have is we have two ways of looking at it. One is the nozzle performance, and another is combustion chamber. Inside combustion chamber, what happens? Combustion happens. Combustion of a propellant happens. So how does that combustion happens? How the propellant burns? So all those things is one study, and another study is uh, performance of the nozzle. So how nozzle is going to accelerate the uh, chemical energy with chemical, we can't say chemical, it's thermal energy. Thermal energy at the inlet of the nozzle to kinetic energy at the exit of the nozzle. So how nozzle is doing that energy conversion from thermal to kinetic. So, and what are the important parameters? How do you design it? What is the uh, performance parameters? How do you characterize this? Is what we did in the week 4, and your assignment is also based on that. So I want to give you small thought about how this course is progressing, and um, how each and every modules you have to link with. So then only you will get a full picture of how this rocket propulsion works. Okay, so having said that, uh, so your week 4 lectures is fully focused on rocket nozzles and performance, right? So what we did in week 4 is, in week 4 lectures, we were finding if I have a combustion chamber pressure and temperature, uh, and I my aim is to get this much thrust and this much specific impulse. So for that, how do I efficiently design a nozzle? What are the parameters affecting the nozzle? So all these parameters is what we studied in the week 4. And uh, so based on that, and keeping in mind the assignment of week 4, I made 3 questions this time. So so that I will solve these three questions so that you will get an idea to solve the remaining assignment problems. Okay, so I mean assignment in the sense quiz. Okay, so having said that, we will start solving today's problem. Okay, so do you have any doubts, anyone? All right. So if there are no more doubts, today we are going to solve a big problems. It requires a lot of calculation. So I encourage you to take your calculators and give me answers as fast as possible. Okay. All right. So what is the first question we have here is we want to design a converging diverging nozzle. So you all know why we need a converging diverging nozzle, right? Because it is going to accelerate the flow from subsonic, which is at the inlet, to supersonic at the exit. We can't have uh, a constant diameter duct, right? So if we have a constant diameter duct, what is going to happen? Let's say I have some duct like this, and from I just attach it to the chamber. Okay, so if I have something like this, what is going to happen? V would be, so whatever velocity with which it comes here, it just goes away. There is no uh, increase or decrease in velocity, right? So uh, this is that is the reason we do not use uh, constant area duct for the nozzle applications. Okay, we use something called converging diverging nozzle, right? So the converging diverging nozzle is going to be attached to the combustion chamber, right? And what are the other things we know about this converging diverging nozzle? We are going to have Mach number equal to 1. We should have Mach number equal to 1. Then only it will be a choked flow, right? And then we will this will be a subsonic portion, and this will be a supersonic portion, right? So we'll be accelerating the fluid inside the nozzle from very low velocity to a high velocity. Why we need a higher velocity at the exit? Because we need high thrust, and also our ISP is depend on velocity, right? So when we have very high velocity at the exit, then our performance is going to be better, and we are going to get a very high thrust, right? So having understand that about the CD nozzle, let's go ahead and read the question again. Design a converging diverging nozzle for optimum thrust at an altitude of 25 kilometers. Okay, and the thrust generated by the rocket at 25-kilometer altitude should be 5 kilonewton. Okay, they are given the thrust. Okay, and then the chamber pressure is 2.07 megapascals, and the temperature of the hot gas inside the chamber is 2880 Kelvin. The ambient pressure at 25 kilometer is 2610 pascals. The mean molecular mass and mean specific heat ratio is this, okay, respectively. So we have a lot of variables here. Okay, let's first write it down, then only we will understand a bit. So what is a given? So we want to let's not altitude doesn't come into picture here anyway. So what we need is we need to generate 5 kilonewton thrust, right? And then what else we know? We know chamber pressure, which is 2.07 megapascals, right? And then we have chamber temperature 2880 Kelvin. Okay, and then what else we have is we have ambient pressure. The ambient pressure is 2610 pascals. This is at 25 kilometer altitude. So we designed the nozzle for that 25 kilometer altitude. Okay. And then we also have mean molecular mass. We write it like MW. Okay. Or you can write it M also. It's up to you. To 23.4 kg per kilomole. So you need to note the, you need to take care of this units correctly. Okay. And then we have specific heat ratio to be 1.3. So, okay, we wrote the given, but we need to understand about this question a little bit. Okay, so what we did last time was we did a three-stage rocket calculation. Right. In that rocket calculations, we found out that I need this much thrust at each and every stage, right? So to generate the thrust, you need to uh, have a proper fuel inside combustion chamber, and you need to combust it, and you need to accelerate through the nozzle, right? In in the nozzle, okay, uh, we i- so we will focus only on the nozzle this time. Okay, in coming weeks we will focus on combustion chamber also. So if I have a nozzle, if I want to design a nozzle for the given thrust, whatever the thrust we calculated for the last time, like for a first stage rocket motor, let's say, and for that first stage rocket motor, what is the we have some thrust, and for that thrust to generate and a given combustion chamber conditions, how should I design my nozzle in order to reach that thrust? Okay, so that is the designing perspective of a on nozzle. Okay, so let's have a sketch here. So this is going to be combustion chamber, and I have attached a nozzle here. So here I have pressure and temperature to be like this, and then we have a nozzle here. So what do I mean by design? So can anyone guess? So what is there to design here? I have given pressure and temperature. What is there to design here? What do I mean by designing a nozzle? Would anyone like to guess? Feel free to talk in between, no problem. Even if the answer is wrong, I'm not going to scold you anymore. We will discuss actually.
So exit area of the nozzle and the throat area of the nozzle.
Wonderful. So these are the design parameters. If we want to design a nozzle, we need to know throat area and we need to know exit area. Or precisely, we need to know diameter of the throat and diameter of the exit. So in fact, you will design a nozzle based on diameter, right? So it's going to be circular, and uh, so we need diameters instead of, like, we need areas also. Area will be used in the calculation for this performance, but diameter is what we design for. Okay, so we need diameter at the exit and diameter of the throat. Okay, so we understood what we need. So to find is diameter of the throat and diameter of the exit. So since you understood the problem, uh, how do we proceed? How can we proceed from here? Just try to find out from where we know. Okay, so what are the parameters we know? What we know is, we know thrust. We know thrust. Thrust is, how do we get thrust? Thrust will be obtained at the exit of the nozzle, right? So somehow we have to get exit parameters from the thrust. Okay. Because we don't know anything about, we also know combustion chamber pressure and temperature. You can also uh, go in this way. Let me know. So how do we proceed with this problem? So using, how do we, the things we know, how do we proceed? You can guess actually. You no need to tell me the equations. You can just tell me we can find this from this from this from this. All right, maybe I will give a clue. Okay, so we know the thrust. This is how I proceeded because there are different way to approach this problem. But how I approached is, I know thrust. What is thrust? Thrust is 5 kilonewton. And what do I know about thrust? Thrust is going to be mass flow rate times velocity at the exit, right? And what we denote velocity at the exit to be jet velocity, right? And can we use how do we use this information? Or else let's do this. We need to know diameter of the throat and diameter of the exit, right? So what is the, maybe we will start with conservation equations. Okay, conservation equations. What we know is, we know mass is conserved, right? So you have to design your nozzle such that it is a choked flow. So mass is conserved. M dot is going to be same everywhere inside the nozzle, right? M dot here and M dot here is going to be same everywhere inside the nozzle. You cannot create or destroy mass, right? So you can write rho of throat, A of throat, V of throat is equal to rho of exit, A at exit and V at exit. Okay, this is what we know. This is one thing we know. So here we have to find this area of exit and area of through, right? These are the two things we need to find, but using this one equation we cannot do it, right? So if we know rho of E, rho of T, and then V of T, in fact V of T also we can get. How do we get V of T? So at the throat it is going to be choked, right? So choked flow means at the throat what is going to be Mach number? Mach number is 1. So if we know temperature there, we can find the velocity there. We basically we can find the speed of sound there, and using speed of sound we can find the velocity there, right? So you can get that. So but for that we need to know velocity at the exit, right? So let's first find velocity at the exit, which is nothing but Vj, Ve both are same. This equation we already saw before, right? What is this equation? So we express velocity, jet velocity or a efflux velocity in terms of combustion chamber pressure and temperature, right? And even molecular weight. So we said molecular weight, light gases will get easily, you can easily accelerate through the nozzle. We also said if we have very big pressure gradient, we will have a very high velocity. Uh, if we have a very high temperature, or if we have high energy at the inlet of the nozzle, we can efficiently convert all those energy into the kinetic energy, right? So based on that, we derived a equation which is nothing but 2 gamma minus 1 gamma by gamma minus 1 r naught Tc by molecular weight of the gases into 1 minus Pe by Pc whole power gamma minus 1 by gamma, right? under root. So this is going to give you exit velocity. This is the exit velocity I will get based on this total energy conversion process. So how do we arrive at this relation? How do we arrive at this relation? There is this fundamental principle we imply.
So, sir, from steady flow energy equation.
Exactly. So it's steady flow energy equation. So SFEE. So this steady flow energy equation is nothing but energy conservation. So at the end of the day, whatever system you analyze, you have to do conservation. Okay. One is mass conservation, which is necessary. Second is momentum conservation. Third is energy conservation. Whatever will it be, it can be rocket, it can be vehicle, it can be two-wheeler, whatever the system be, you have to do only these three conservation uh, for that system, and you are going to end up solving the problem. Okay, so we use energy conservation as Mohammed said, and then uh, we arrived at this relation, right? Please go and revise it if you don't remember. Okay, so here do we have all the parameters here? So we have we know or not, we know gamma is given, and we know molecular weight. We also know temperature of the chamber, right? And then we know chamber pressure, right? Do we know the pressure at the exit, ambient pressure? Do we know pressure at the exit? What is the pressure at the exit? How do we find it? Or maybe can anyone guess what will be the pressure at the exit? Will it be PA?
Yes, sir.
So why it will be PA? Why it should be PA? These are few subtle things you need to tell. You need to remember, in fact. So when you design a nozzle, okay, so you are going to design a nozzle to obtain optimum thrust, right? To obtain optimum thrust, what you have to do, you have to expand your nozzle to the ambient pressure, right? So that is the reason the ambient pressure is 2610 megapascal, and if you are able to get the exit pressure of the gases to be 2610 pascals, then you are going to get an optimum thrust at that altitude. So this is at the altitude 25 kilometer. So when you design a nozzle, you will tell that at this altitude my ambient pressure is 2610 kilopascal. So I want exit pressure to be to 2610 kilopascal. Okay, 1610, sorry, pascals. Okay, so now you know everything here. P, so P is also known. So can someone quickly do the calculation and let me know what is the result? It's a little bit bigger calculation. So 2 into gamma is going to be 1.3 divided by 1.3 minus 1, right? And then R is 8.3145. And what is the temperature here? 2880 Kelvin divided by molecular weight. So question to you guys. Should it be 23.4? 23.14 kilogram per kilomole is 0.14 or something else. Here it is megapascal. So 6, right? And then 3 minus 1 by 1.3. Should it be 23.4? You can quickly do the units. What is the unit of R naught? R naught is going to be the joules per mole Kelvin, right? Times Kelvin. So Kelvin gets cancelled, divided by, what is this? Kg per kilomole. So we cannot simply cancel this, right? So maybe we need to write it like 10 power 3 times mole. So then here we should have 10 power minus 3, right? So this is 23.4 divided by 10 power 3. So if it comes up 10 power into 10 power minus 3. So this is something you need to take care carefully. So in your assignments also there will be uh, few parameters which will be given in a different unit. You need to uh, input it appropriately. Okay. So what is the velocity you guys are getting? I didn't solve the problem. I just took the questions. That's why I'm asking you guys. What is the solution you are getting?
So 2.63 kilometer per second.
Okay, wonderful. 2.63 kilometers per second.
Second.
Right, right. So this is actually in the range. If you just simply look at it, if your calculations are right, it will be around this range for whatever the rocket you take. It's going to be in kilometers per second. It can be 1 or 2 kilometers per second. So yeah, exit velocity is going to be 2.63 kilometers per second. Let's make it Vj. Okay, and so we found Vj. What we have is we have this thrust equation. We can substitute it and get the m dot, right? We know what is the mass flow rate happening inside the nozzle. So mass flow rate is nothing but T by Vj. T is nothing but how much is T? 5 kilonewton, right? So 5 into 10 power 3 divided by 2.63 into 10 power 3. So what is the mass flow rate? So I am getting around 1.901. Is it right?
Yes, sir. Right.
So we found the mass flow rate, but what we need, what we need is we need the area of throat and area of the exit, right? So how do we go about? So we have this mass conservation equation. Okay. So we know m dot, we know ve. We need to find ae, right? How do we find rho e? Either we can go in this with this equation, or you can use this equation. So before finding area at the exit, you can find the area at the throat. How do we find area at the throat? So for that we need to know rho t and vt, right? So we did all these calculations, we derived all these things, and we came up with a simplified expression. Is it's going to be gamma times PCAT divided by square root of RTC times 2 by 1 whole power gamma times gamma minus 1. So we arrived at this relation in terms of what we know. We know chamber pressure, we know chamber temperature, and we know gamma of the gases, right? Based on that, we came up with this. Okay, so now you can substitute the, and one more thing you need to note is where is the velocity term, right? Where is velocity in this? Or maybe you might need to be Mach number. You may need to look for Mach number in this relation. Where is Mach number in this relation? There is no Mach number in this relation. But what we know is this is for only choked flow, right? In the choked flow, what we know is we know Mach number is equal to 1. So we substituted in that relation whatever we got, and then we arrived at this simplified expression for the choked flow. So you need to understand that this expression is only for choked flow. So the if it is not a choked flow, the general expression for mass flow rate would be little bit different. How would it be different? So you can go and revisit the lectures to get the mass flow rate of non-choked flow, so to say. Okay. So let's start plugging in the values. So what is gamma here? We have gamma to be 1.3. 1.3 into 2.07 megapascals 10 power 6 times area of throat, which we don't know, divided by square root of R is 8.3145, and then temperature should be in Kelvin 2880, and then 2 divided by 1.3 plus 1 power 1.3 plus 1 divided by 2 times 1.3 minus 1. Alright. What is m dot? M dot we just calculated. It is going to be 1.910. Okay. So uh, you can rearrange this equation and you can get the throat area. How do we get throat area? So what is the throat area? Can you guys quickly do this calculation? Maybe I will also do parallelly. I will check your calculations. 0.3 minus 1 is 0.3. 0.3 into 2 is 0.6. Okay. 0.90. I'm getting some weird answer. Did anyone get any answer? What is the answer you guys are getting?
The 2.12, 10 power minus 4.
I see. Wow, yeah, I think I made a mistake here. So this is R, right? What is R? R is not universal gas constant. R
Yes, sir.
naught is
Yes.
universal gas constant. So we need to calculate R first. Now what is R? R naught by molecular weight. So can you update this and let me know what is the?
Yeah.
So it is going to be 8.3145 divided by molecular weight, which is 23.4 into 10 power minus 3. Okay. So what we will do is we will write this molecular weight in terms of kg per mole. Way to avoid this mistake is to express everything in terms of SI units and then go forward with the calculations. Okay. And also you need to take care of whether it substitute it here. Basically you just need to multiply by square root of 223, right? So he was getting 2.1 into 10 to minus 4. Maybe we should divide. How much are you getting?
So 1.39. into 10 power minus 3.
Yes, 1.39 into 10 power minus 3 meter square,
Meter square.
right? So we know the area of throat now. So area of the throat is 1.39. From there we can find the diameter, right? So we will just do pi by 4 dt square. This is the area of the circle. Um, so what is the dt you are getting? 0.39 10 power minus 3 into 4. Looks like everyone kept, except Mohammed, everyone kept their calculator away. Okay. Mohammed, did you get any results? What is the diameter you're getting? I am getting 0.
Sir, 0. Yes, sir, 0.042.
Okay, thank you, Mohammed. Uh, yeah, so diameter of the throat we found. Uh, uh, Now we need to find the diameter of the exit, right? How do we find the diameter of the exit? We actually derived a very important uh, relation from throat to exit in the classes. So let me remind you, it is going to be expansion ratio, right? I think it is AE by AT, if I remember correctly. And we write this relation, that expansion ratio, to be a little bit complex relation which has a lot of gammas in it, and gamma minus 1 and PC by PE power 1 by gamma divided by square root of, I hope everyone have these relations, right? 1 minus gamma, 1 minus PE by PC. So note the change in ratio, pressure ratio. So numerator is PC by PE, denominator is PE by PC. Alright. So let's just substitute the values here again. 2 by 1.3 plus 1 is 2.3. By 1.3 minus 1 is 0.3. Then PC 2.07 megapascals divided by 2610 pascals. 1 divided by 1.3 divided by square root of 3 by zero point 0.3. 1 minus P, which is 2610 divided by PC, 2.07 into 10 power 6, and 0.3 by 1.3. Alright, this will give you an expansion ratio, which is AE by AT. Since we already know AT, we can just simply find AE. Okay, what is the expansion ratio you are getting? Is someone else also calculating? I don't know whether everyone is calculating, or maybe calculator is not near you.
Sir, I am getting 291.07.
Okay, 2.2.
291.07 I am getting.
291.07. Okay, I think it is quite high, right?
Yes, sir. Yes, sir, I will just check it.
Okay. Maybe I will also do the calculation once. Um, 3 power 1 divided by 3. Numerator I'm getting 106. 6.64. 10 power 6. 10 power 6. 0.3. So denominator I'm getting around 2.454.
So finally, I'm getting 43.45, sir. I just made mistake on numerator.
No problem. 43.45.
45.
Okay, that actually within the range. Okay, so uh, 43.45. So now we can find exit area, which is 43.45 times area of throat, right? So what is area of throat? Area of throat we found 1.39 into 10 power minus 3. So if we do that quick calculation, how much are you guys getting?
60.49 into 10 power minus 3.
Okay, 60.4 into 10 power minus 3, and this is going to be meter square. Okay, did I wrote that? Meter square. And this area of exit is going to be pi by 4 dE square, right? And if we do that calculation, what is the diameter of the exit you are getting?
0.277 meter.
0.277 meters. Okay, wonderful. So we found the exit diameter, and we also found the throat diameter. And what are the inputs we had? We had thrust, how much thrust I need to generate, and what is the optimum altitude for which I designed the nozzle, and then third is what is my combustion chamber conditions. Okay, using these three parameters you can design your nozzle. Design in the sense the exit diameter and the throat diameter. Okay, so that is key takeaways in this uh, problem. Okay, so the answer is diameter is going to be maybe 42 mm, and exit diameter is 277 mm. So 42 mm and 277 mm. Yeah, you can imagine, which also makes sense. Anyway, so having understand how do we design the nozzle, let's go forward with performance. Okay, so now we have another interesting question. So here we are going to deal with calculating this performance parameters like characteristic velocities, thrust coefficients, and specific impulse from there. Okay, so uh, yeah, I will explain you by explaining the questions. So the question is, a solid propellant is formulated to generate hot gas at a temperature of 3100 Kelvin. Okay, so yeah, there is some propellant, whether it will be solid or liquid. At this point of time, we don't really care, but what we care is we care about the temperature of the chamber, because that is going to directly affect the exit velocity and the performance of the nozzle. Okay, so the temperature of chamber is 3100 Kelvin. The molecular mass of the gases is 23 kilogram per kilomole, and the specific heat ratios are given. Now the combustion chamber is having combustion chamber pressure. Actually, there is a pressure missing. Combustion chamber pressure is 7 megapascals. Okay, so tot- we fully defined the combustion chamber. Combustion chamber has a pressure of 7 megapascal, temperature of 3100 Kelvin, and the gases have a molecular mass of 23 kilogram per kilomole, and we also have a specific heat ratio of 1.34. Okay, so in combustion chamber side, everything is defined. Now the gases are expanded in the nozzle to ambient pressure of zero point 0.1 megapascal. So ambient pressure is given 0.1 megapascal. We were asked to find the characteristic velocity, optimum thrust coefficient, and ideal specific impulse. And then we are also asked to determine the rate at which the propellant must burn. So, what is the rate at which the propellant must burn in order to generate the thrust of 1 meganewton? So, we need to generate thrust of 1 meganewton, and based on the performance parameters of the nozzle, we are going to uh, find out what is the rate at which this propellant must burn in order to get the thrust. Okay, so you can also assume a C star efficiency of 0.7 and thrust coefficient. So we'll come to this second part later. First we will try to understand and find these parameters of a rocket. Okay, so let's, as usual, we'll write the given. So it's going to be chamber pressure and chamber temperature we know, which is going to be 3100 Kelvin, and chamber pressure is going to be 7 megapascal, right? And molecular weight is going to be 23 kilogram per kilomole. Okay, so we'll quickly express this in terms of our notation. It's going to be kilogram per mole. Okay, so that we don't do any mistakes. Okay, then gamma is going to be 1.34. All right, and then we also tell that I'm going to expand it to ambient pressure of 1.1 megapascals. All right, now uh, we have to calculate characteristic velocity, which is C star. C star is called characteristic velocity. Please understand this characteristic velocity, specific impulse, uh, and thrust. These are the few main performance parameters of any propulsion system. So C star is going to tell us about the it's actually a metric for combustion chamber. Even if it is named as characteristic velocity, uh, it is actually a metric for combustion chamber. Okay, and then CF, there is thrust coefficient, which also we need to find out, right? Find C star, we need to find CF, and then we need to find ISP. Okay, that is the first part of the question. So the C star is going to be a metric for combustion chamber. CF is going to be a metric for it's a metric of performance for nozzle. Okay, and then ISP is your full propulsion system. Okay, what is the performance of your propulsion system is going to be uh, you will express your performance in terms of these three parameters. Okay, and of course we need thrust also in order to have a in order to based on your payload and other things. Okay, so these are the performance keeping in mind of performance, these are the parameters which you need to take care in any propulsion system or a rocket. Okay, so how do we find C star? So what we know about C star, we already have some relations, I guess. So can you guys recall how did we uh, arrive at an expression for C star? So I am just writing down the expression. It is nothing but 1 by capital gamma times 1 naught Tc by molecular weight, where this gamma is going to be square root of gamma times 2 by gamma plus 1 power 1 by 2 times gamma minus 1. Okay, so we have the, I gave you the formulas also, but how did we come up with this expression? The C star, how did we get this expression? Can anyone guess? Can anyone recall what happened in the lecture? So that it would be easy to understand. No problem. I recommend you to go and recall, so that we can understand this performance metric. So basically, what we did was we derived a expression for m dot, right? So there is this m dot which is actually a function of we derived it. I mean, we even used it in the last uh, problem. We derived it in terms of uh, the chamber pressure, area of the throat, and then the chamber temperature, right? So that is what we did here. So if you look at this, we derived at this equation. How did we get this equation? We did the mass conservation, or let's say mass flow rate is equal to rho T AT Vt, where rho T and Vt are calculated based on making it a choked flow. Mach number is equal to 1. Substituting all those relation, and rho T is nothing but uh, pressure at the throat by R into T at the throat, and we express pressure at the throat in terms of chamber pressure, right? Based on this, we had this converging flow, right? The converging diverging flow, right? And then this is chamber pressure, this is pressure at the throat. We express this in terms of chamber pressure, and we substituted it, and we arrived at this equation. And if you look at this equation, this part is called gamma, which we separately wrote here, and this gave us some insightful result, like it depends on chamber pressure. So chamber pressure is nothing but m dot into square root of RTC divided by gamma times AT, right? So it is telling that if I want, I need to have a choke flow and I need this much mass flow rate to generate this much thrust, and if I have this much mass flow rate, what should be my combustion chamber pressure? Okay, so it is actually telling, I mean, you can actually calculate combustion chamber pressure using these relations, and you can say my combustion chamber pressure should be this much. Then if I need to have combustion chamber pressure this much, then I will use the propellant, different propellants, their burning rates. I will calculate those burning rates accordingly. Okay, so I will select the propellant based on this, how much chamber pressure and temperature I need. Okay, so and then we arrived at this relation. How did we arrive? So we took area of the throat also this side, so we wrote PCAT by m dot is equal to square root of RTC by gamma, and then we denoted this to be C star. So in order to have this mass flow rate, uh, and I have this chamber pressure, then I have C star velocity to be like this. So this is actually a metric for chamber, combustion chamber. It is not a metric, even though it says velocity, it doesn't mean it is a metric for nozzle. So that is something you need to understand. So please go and revisit if you do not understand the lectures, and come back to me if you have any doubts. Okay. So for today, what we will do, we will use this relation, okay, and then we will calculate the C star velocity, and then we'll see what happens. Okay. So gamma is going to be, we have a different gamma in this problem. We have 3 4, okay, and then 2 divided by 1.34 plus 1 Then we have 2.34 divided by 2 times 0.34. Okay. How much is this capital gamma is coming?
0.67.
So getting 0.67. Wonderful. 0.674 I'm getting anyway. And then let's say we will substitute it here, 0.674 or 67. Square root of R naught is going to be 8.3145 into TC. What is the TC? 3100 Kelvin, right? 3100 divided by molecular weight is 23 into 10 power minus 3. What is the velocity you are getting?
1.57 kilometer per second.
One, okay, 1.57 kilometers per second. Okay, all right. We have a C star velocity to be 1.57 kilometers per second. Now you have to calculate thrust coefficient. Okay, so what is the relation for that? In this nozzle performance, the relations are going to be very very big, but uh, the concepts it's not that tough. Okay, so do you guys know what is the relation? Okay, as usual I will write the relation, no problem. Divided by gamma minus 1, 2 by gamma plus 1, gamma plus 1 by gamma minus 1. PE by PC whole power gamma minus 1 by gamma. Then we have a square root also. We have PE by PC minus PA by PC times AE by AT. Okay, so this is the CF. So do we know everything in this? Do we know everything in this relation? What we don't know AE, we don't know AT, right? We don't know PE, right? PA is only given. Okay, ambient pressure is given, but the exit pressure we don't know. How do we go about? You need to understand what is asked. Yeah, yeah. Please go ahead.
So the exit pressure will be same as ambient pressure. I
Why it
think.
should be exit pressure will be same as ambient pressure? It can be different, right?
So the gases are expanded in the nozzle to the ambient pressure.
Yeah, you are
Ambient
telling
pressure.
we can make an assumption, right?
Yes, sir.
Okay, so
Actually,
uh,
the in problem they are given, sir.
okay, yeah. Actually, in the problem, it gases are expanded nozzle to the ambient pressure. Uh, that is true, and we also asked to get optimum thrust coefficient. Okay, so optimum thrust coefficient, what does it mean? It means the gases are expanded till the to the ambient pressure. Okay, so what happens is P is equal to PA again, which means this term goes away. So we no need to worry whether AE AT is given or not. Okay, uh, and then this PE will be replaced by PA. All right, let's do this problem. Let's solve this. 1.34 square divided by 1.34 minus 1, 2 by 1.34 plus 1. So this is going to be 2.34 divided by gamma minus 1 is 0.34. 1 minus P is ambient pressure, right? 0.1 megapascal, 10 power 6 divided by what is chamber pressure? Chamber pressure is 7 megapascal. 6 power gamma minus 1 is 0.34 by 1.34. What is the thrust coefficient you are getting?
Sir, I'm getting 1.53.
Okay, 1 point
537.
1 point
1.537. 537.
okay 537. Okay, let me check. We got CF. I also got the same results. CF to be 1.537. Okay, and we also find C star to be 1.57 kilometers per second. All right. Now we need to find specific impulse. How do we find specific impulse? We calculated something else, and we suddenly ask what is specific impulse. This equation you all should know, right? What is the specific impulse? How do we calculate it? What is the equation we use? Based on the available information, we have C star and CF. Chamber pressure, temperatures. How do we calculate specific impulse? Actually, two ways of calculating specific impulse. For example, for like like for this problem, in fact, most elegant way is specific impulse is nothing but C star times thrust coefficient. One is combustion chamber, one is a nozzle performance. Together, it is going to give us rocket performance. Okay, so that is what a significance of this equation. Okay, uh, but we can also derive it. So how do we derive? We know it to be F by FTT is the impulse, right? Impulse by mass of the propellant, right? So what we know about C star? C star is nothing but CCAT by m dot, right? And what is CF? CF is nothing but F by PCAT. You guys should go and look back at the relations. So when you multiply these two, what happens? These two cancels, gives us F by m dot. Alright, and this is nothing but F by m dot. That is how we get specific impulse. Okay, and there is also one more way. We also told that specific impulse to be equal to velocity of the exit velocity. Okay, and to find exit velocity is a function of what? Molecular weight, temperature of the chamber, and then chamber pressure, right? But this thrust coefficient we calculated is optimal. It doesn't uh, tell you if the nozzle is under expanded or over expanded. It tells that uh, it doesn't. It is not for under expanded or over expanded nozzle, because we assume that it is fully expanded, ideally expanded. So there is no uh, pressure thrust which is going to act. So if there is a pressure thrust acting, this CF will be something else and this ISP will be something else. It will not be equal to whatever you calculate here, because this relation also assumes that exit pressure is actually equal to ambient pressure. It doesn't, we actually say that this is not exactly equal to, it is actually almost equal to exit velocity. It is not. This is also a way of measuring the specific impulse. That is what we say. But this is the accurate way, C star times CF. Okay, so what is it you are getting? C star is going to be 1.57 kilometers per second, and then CF is going to be 1.537. Calculation. What is the ISP? I'm getting 2.4131.
It's a 2.4.
Okay, very good. Thank you. ISP is going to be 2.4131 kilometers per second. Okay. So usually the solid propellants actually have this specific impulse around this only. So you will learn more about solid propellants in coming lectures. Okay. So we also express this in terms of seconds. If we express this, if you want to express specific impulse in terms of seconds, how do we write? So whatever we got, we have to just divide it by G naught, which is 9.81. Alright. So if we do that, what happens? It will give, it's going to give me 246 seconds. So usually some people usually follow meters per second as a specific impulse. Some people usually follow seconds. Uh, Basically they say it's force thrust generated per unit weight flow rate. Here we wrote in terms of mass flow rate, right? ISP is this ISP, let's write it dash, thrust generated in terms of weight flow rate of propellant, WP, which is nothing but F by m dot into G naught. Okay, so per unit, uh, if we write specific here, we wrote in terms of thrust by m dot. Okay, so usually what I want to convey is usually. For solid propellant, so the specific impulse is going to be around 246 seconds, and the R of kilometers per second, it is going to be around 2400 kilometers per second. So in that way we can, so based on my knowledge I'm telling this, in that way we can say, since we are calculating for solid propellant, we should expect these results. Anyway, okay. So having done this performance calculation, so do you guys have any doubts in this performance calculation? Whatever we did for last two uh, problems? Anyone? Can someone say yes, no? So they were around, it's around six people.
No, sir.
Okay, you don't have Mohammed. Thanks, Mohammed. You are the savior for me today.
No, sir. Thank you, sir.
So others are very silent. I don't know why. Is it all? Uh, no problem. Feel free to interrupt me anytime. If you don't know, I can explain you once more. Okay. So this is so we finished two problems. The third problem is going to be something for you to understand the concept of this performance. How does this performance depends on the uh, various parameters. Okay, so this is quite easy problem. You guys can easily calculate it. Okay, we have what we have here is the C star for composite propellant is 2200 meter per second. So they directly gave a C star velocity, and they say it's a composite propellant. Composite propellant is nothing but solid propellant, solid composite only they say, because we will have a fuel and we will have an oxidizer. It gets we have uh, different species, and we get species in the sense. Say the ammonium perchlorate and HTPB propellant, let's say, we have different molecules or different fuels and oxidizer. We get mixed it and we come up with a solid like consistency, and then we will cast it in the rocket motor. We usually call solid propellant propulsion system to be rocket motor. Okay, so here what we have is it's a composite propellant because it has a lot of like sometimes you will add energetic materials to that composition in order to have a very good performance. That's why it's called composite propellant. So uh, the C star of a composite propellant is 2200 meter per second, and the combustion products of this propellant have the molecular mass of this much. So molecular mass is given, and then we have a temperature of the chamber temperature is going to be 2600 Kelvin. Okay, and then what uh, we did is in this composite propellant, aluminum powder is added to the above propellant to improve its specific impulse. So aluminum is nothing. Aluminum is a uh, it's actually energetic. Uh, how do I say? It's actually energetic material added to the propellant. So we use aluminum every day, right? So usually this metal uh, particles, or let's say metals, usually have high energy content within it. So if you combust them, you're going to get a very high release of energy. That's why these aluminum, boron, and few more energetic materials, these aluminums have energy more than a TNT. For example, TNT or RDX explosions have released a lot of energy, right? So compared to that, aluminum has more energy in it. So that's why they add it as an energetic material to that propellant in order to boost its performance. Okay. So here we have aluminum powder is added to the above propellant to improve its specific impulse. So they are going to improve its specific impulse. But what happened is when they added it, the molecular mass of products increases. So from 22, it increased to 24. So upon combustion, the gases has some molecular mass, right? Gas is a mixture of lot of elements. So it is going to have a molecular mass, and that molecular mass has increased from 22 to 24. And but in addition, the temperature also increased from 2600 to 3200 Kelvin. Okay. Uh, so, if the specific heat ratio of combustion products of aluminized and non-aluminized propellant remains same, determine the C star of aluminized propellant. So they are given one propellant which is not aluminized, which means there's no energetic material like aluminum powder is added, and there is another propellant where they took the same propellant and added aluminum powder and got some different uh, temperatures and molecular weight. So based on that, we are asked to calculate what would be the C star of this propellant. Uh, okay, let's do that. And one more thing, I think we didn't do one of the. Okay, we didn't do this. We'll come to that later. Okay, I also forgot. So let's finish this one. This is the easier. So we what we have given is we have something called non-aluminized propellant. Let's write that non-aluminized propellant, and non-aluminized propellants as C star or 3. Let's call it 1. Okay, C star is going to be 2,200 meters per second, and then temperature is 2,600 Kelvin, and molecular weight, a molecular mass is going to be 22 kg per kilomole. Okay, which is nothing but 22 into 10 power minus 3 kg per mole. Then we have aluminized propellant. Here we have C star, let's call it C2, which we don't know, which we are asked to find out, right? And then what has been observed is it is gave a rise of around 600 kelvins, and also molecular weight is also higher, around 24 10 power minus 3 kg per mole. Okay, right? So we understood this. So now, how do we find C star of second propellant? Do anyone have any idea how to do it? Your information, let me write down the relation of C star in terms of T and molecular weight. It is 1 divided by gamma times square root of RT by molecular weight. How do we go about? And one more thing we forgot is gamma 1 gamma 1 is equal to gamma 2 is equal to gamma. They're basically telling it is same specific heat. So specific heat ratio is not changing upon adding aluminum powder. So let's write what is this gamma. So gamma is, please let me know how do you approach this problem. It's so silent except Mohammed. Maybe I will start calling names. Uh, we have Aishwarya, we have Arini here, we have Iran here, Iram here, we have Satish here, we have Padmavati here, we have Srini here. All right, anyone? How do we find the C star of alumnus propellant? How do we find it? Can we just simply find it? So let's write C2 star is equal to 1 by gamma square root T2 divided by molecular weight of 2. It looks like we know everything, right? So we know T2, we know molecular weight, we know R naught. Do we know gamma? Gamma we didn't get, we don't know. Gamma is not given. Gamma, they said gamma is same for both propellant, but gamma is not given, right? What you can do is You can find gamma first from the first propellant, and then you can use that gamma for the second propellant. That is one way, but it is a very uh, like it requires a lot of calculation, right? So we no need to do that. What we could do is we can write C1 star separately. What is C1 star? C1 star is going to be 1 by gamma square root of R naught T1 divided by molecular weight of 1. This we know, right? And then what is C2 star? C2 star is going to be 1 by gamma square root of R naught T2 by molecular weight of 2, right? What we do is we just divide these two equations. C1 star divided by C2 star is going to be 1 divided by gamma square root of R naught T1 by molecular weight of 1 divided by R naught T2 molecular weight of 2. So what we know is we know gamma is going to be same, so we can just cancel this. And R naught is universal gas constant, so we can do that also. So what it boils down is square root of T1 by molecular weight of 1 times molecular weight of 2 divided by T2. Or in other words, C1 star by C2 star is nothing but square root of T1 by T2 and square root of molecular weight of 2 by molecular weight of 1. So now you can easily calculate because we know all the four here, and C1 star by C2 star we can calculate, and once you calculate that fraction you can easily find C2 star, right? So let's do that, which is going to be square root of T1 is going to be T, T2 is higher, so T1 is 2600 divided by 3200, and then square root of molecular weight of 2, which is 24 divided by 22 into 10 power minus 3, but it gets cancelled. Alright, so what is C1 star by C2 star you guys are getting?
Zero 0.941.
Much? 0.941, is it? Okay. So let's calculate C2. How much is it?
0.94.
Is it 0.941 or something else? So this is right, right? I didn't get you. You were breaking.
Yes, sir, I'm getting 0.941. Actually, in my area, network is problem, sir.
That is fine. So
Uh,
how much is C2 star?
uh, that's why you're getting big noise.
Yeah, no problem. But how much is C2 star? How much you are getting? We have to find C2 star, right? So we'll just divide it by 0.941. Mm, So we have 2200 meters per second divided by 0.941. It is probably it will be around 2300, I guess. Right, 2337.9 meters per second I'm getting. Can write it like 2.34 kilometers per second. Yeah. So the things to understand here is, sorry, C2. So your C1 star was 2.2 kilometers per second, and upon addition of aluminum, what we added aluminum to our propellant. Upon addition of aluminum, what we had was we saw a change of around zero point 0.1 kilometer per second in our velocity, C star velocity, which means the the performance of combustion chamber has improved. If the performance of combustion chamber is improved, what is going to happen? Performance of specific impulse is going to improve. Okay, so if the specific impulse is improved, even if a small change like 10 second or 100 meter per second specific impulse is improved, it is going to drastically reduce your propellant weight you are going to carry in the rocket. So that is the reason it is very important. The, the C star, CF and ISP is very important for any rocket system. Okay, so do anyone have any questions? All right, if we don't have any question, let's complete the previous problem. To recap.
Sir, for second question, we need to calculate.
Right, right. So we need to calculate this mass flow rate, right? Yeah. Let's calculate this mass flow rate. Okay. We need to calculate this. We need to calculate mass flow rate. So what we know till now is C star. C star is nothing but 1.57 kilometer per second. CF is 1.53, I guess, 537. And then we have specific impulse to be 2.41 kilometer per second. Okay. So actually I'm telling mass flow rate. Is mass flow rate what we want to find? What is given? We need to find rate at which propellant must burn, right? So mass flow rate is nothing but mass flow rate of propellant, or in the sense upon combustion. Yes, go ahead. Okay. So upon combustion, what happens is we are converting the propellant to gas, right? Or the reactants to products, right? If you see it as a chemical reaction, the propellant is converted into gaseous products, and along this process, mass is conserved. So the rate at which propellant is burned is the rate at which it is going to uh, come out of the nozzle. So if you remember what we wrote in specific impulse, the specific impulse is nothing but thrust, right? Thrust is nothing but thrust of force divided by mass flow rate of propellant. Okay. So we want to calculate this mass flow rate only. Okay. So uh, how do we calculate? This is ISP is nothing but F by MP. What is also given in the equation, in the question, is that you are asked to assume a C star efficiency of 0.97 and the thrust coefficient of 1.2, right? So let's just write that also. So C star efficiency, let's write efficiency C star is nothing but 0.97, and thrust coefficient, how do you write thrust coefficient? I don't know. Is it followed delta? Right. thrust zeta. Okay, it's nothing but one, which is this 1.2. Okay, so we have given two efficiencies. Okay, one is efficiency, one is a thrust correction factor. So this, how did we define this efficiency? We defined it as C star of ideal, what we calculate, and then C star of actual. Okay. Similarly, this thrust coefficient is nothing but CF ideal, CF ideal or actual, CF actual, because it is greater than 1.2, which means that actual is usually less than ideal. So if it is greater, then it should be the uh, numerator. Okay, so 1.2 is CF actual by ideal. Okay, so what we have to do is we need to calculate C star actual, okay, and then CF actual, and based on this CF actual, we will based on these two actual performance parameters, we will calculate specific impulse, which is also actual specific impulse. And once you find actual specific impulse, we know this much thrust needs to be produced, which is 1 megaton, right? 1 mega newton, 1 mega newton, which is nothing but 1 into 10 power 6 newtons, right? We know this much mass thrust has to be produced. Then you can find the from specific impulse, you can find the mass flow rate of the propellant. That is going to be mass flow rate of the gaseous, that is going to be equal to mass burn rate of the propellant at the combustion chamber. Okay, having understand that, what we will do is we will find C star actual, which is nothing but C star ideal divided by efficiency. How much is this coming out to be? C star ideal we just found out is 1.57 divided by 0.97, and this is going to be CF actual. It's nothing but 1.2 times CF ideal. CF ideal is we got 1.537. CF actual will get. Then what we will find? We will find final ISP, which is also actual, which is nothing but C star actual times CF actual, which is actually equal to F divided by M dot of propellant. Okay, let's write it down. What is the C star actual you're getting? It's 1.57. Sure. 1.618. It's more than ideal. Then our equation is wrong.
1.618, sir.
Yeah, but it is more than ideal, right? It cannot be more than ideal. It can be should be less than ideal. So it is actually C star actual by ideal. I wrote it wrongly. So then what you will have multiplied by efficiency. Hence 0.7 times 1.57. How much is you are getting? No. These calculations are quick, right? Maybe let's ask someone else also. Satish, would you like to answer? Anyone else? Iram? Harini? Uh, Aishwarya? All right. Maybe people are sleeping. It's fine. Mohammed, give me the answer. What is the answer you're getting? I'm getting 15229 kilometers per second.
Sir, myself also 1.5229, sir.
Thank you, Satish. How about CF actual?
1 minute, sir.
CF actual.
1.8444.
Okay, thank you. And then how much is ISP actual is coming?
2.8088.
0.8088. Okay, so we need to produce 1 mega newton, right? So it is going to be, how much is mega? 6, right? Divided by m dot of p. So how much is this m dot of p? 10 power 6 divided by answer.
2.8 into 10 raised to the power minus 6.
2.8. Oh, okay. Shouldn't it be coming in the division?
Sir, sorry, it would be 356023.9
If I 6 0
to 3.9.
3.9, isn't it very high, right? Let's check whether we did some mistake. We are getting C star to be very high. CF is high. Mass flow rate this much is very high. Okay. So what do you guys think? Did we make any mistakes? I mean, I only gave the relation, so if there is a mistake in relation, we can't do anything. Please cross check my relations also. Let's cross check relation. I don't know. I feel it is very big. Maybe maybe the question is made like that. I don't know. Yeah, it's better you guys cross check this calculation once because it is coming very big. Let me open where is C star. C star is nothing but 1 by gamma square root of r naught Tc by 1/8. Okay, gamma is nothing but square root 1 plus 1 between the 1. This is fine. Then we have 100 divided by 23, 10 power minus 3. Okay, C star is coming right. Then CF is also right. CF, let's check CF also. Please let me know if we made any mistake in this problem. Okay. So what is CF? Let me just check the relation I gave. This PE by PC. That is fine. It looks everything is fine only. Maybe something problem with the question itself. All right, no problem. So please recheck these relations and calculate it once again and see. Uh, Basically, ISP came out to be around same only. 246 seconds is what we usually observe in a solid propellant. Uh, Sure about this m dot. M dot is too high. 356 tons per second. What about something? This is kilometers per second, right? Into 10 power 3. So this becomes, I think it will be 356.023 kg per second. Now it makes sense. Yeah. Now we got the mass flow rate of propellant to be around 356 kg per second. Still, it is high. Uh, it's very difficult to imagine how much kg per second is. This much kg per second is difficult to imagine. But uh, what I wanted to say is, uh, we are. I mean, we can calculate what is the mass flow rate of propellant or the rate at which the propellant should burn uh, to meet this much thrust. So this is basically important parameter when you choose a propellant. Okay. So because if you take a propellant, let's say a simple propellant or let's say simple fuel, which burns very slowly. Okay. Like I don't know. The rocket, let's say Diwali rocket, if you take. I'm not sure how much rate, at which rate it burns, but let's say it burns, if it burns slowly, okay. So we are not going to reach, we are not going to give that much mass flow rate. Then if we don't give enough mass flow rate, we are not going to get enough velocity at the exit. If we don't get enough velocity at the exit, we are not going to get the thrust. So in order to give that thrust, your propellant has to burn at certain rate, okay, and when it burns at certain rate, it has to it will give the desired thrust. So that is how we design any rocket motor also. So last class we say we told that we will have different stages, and different stages will produce this much thrust. This based on today's discussion, what we are going to say is, to get this thrust, what should be my nozzle design, and in addition, in order to get this thrust, what should be my combustion chamber performance and nozzle performance? When you go to combustion chamber performance, what is the rate? Uh, what is the combustion chamber C star velocity? What is the combustion chamber pressure and temperature I need, and also the rate at which propellant burns. So we are trying to decide at which rate this propellant should burn. Okay, and based on that we will uh, take the propellant. Okay, we will choose the propellant. For example, some propellant will be very which has very less burning rate, and some propellant will be have more burning rate. In fact, if you take explosion TNT or RDS, it is going to have uh, burning rate which is very high. Okay, so it cannot be used in the rocket motor because that burning rate is very high, and your mass flow rate is choked by the nozzle, so you cannot have more mass flow rate other than that. This will give rise to increase in chamber pressure of your uh, rocket, and as soon as it increases the chamber pressure, the pressure exceeds the design pressure and it bursts. Okay, and also the explosion is very rapid. You don't want rapid explosion. You don't want to combust all the propellant in a second, right? You need to reach the certain altitude, so you need a certain rate which should not be very less, it should not be very high also. So we will select the propellant based on that. Okay, so in upcoming classes you will see how you will select a propellant, and there are few parameters in which this is also one of the parameter. Okay, all right. So once you have understood that, I think I covered all the relations and all the topics which has been discussed in week 4, and I hope this would be helpful for you to solve the assignment, quiz 4. Okay, so please let me know if you have any questions. By this I will stop today's sessions. Okay.
Sir, you can brief the question number 1 briefly, sir. Actually, I have not
Okay.
attended.
Okay, no problem. In question 1, what we did is we designed a CD nozzle. Okay, so in question 1, we designed a CD nozzle to obtain a certain thrust. So in last class, what we did was we did. I hope you attended last class. I don't know.
I am not there, sir.
In last class, what we did was we did a stage calculation. Like in each and every stage, how much thrust I need, we
Okay.
calculated that. Okay, so
Okay.
in order to achieve this thrust, I have to design my nozzle. I have to design my combustion chamber nozzle. I have to design the whole rocket. But this week's focus is on designing the nozzle. Okay, so what we did here was we need to design a converging diverging nozzle in order to get optimum thrust at an altitude of 25 kilometer. Okay, so what we had was how much thrust we need to generate is 5 kilonewton. Okay, and the chamber pressure, the inside the chamber, the combustion chamber pressure is given. Combustion chamber pressure and temperature is given. Okay,
Okay, sir.
and then ambient pressure is also given. So basically, what we are given is chamber pressure, chamber temperature, and then
Okay.
uh, ambient pressure also. So you need to obtain a certain thrust at the exit of the nozzle. To attain that thrust, you need to design the nozzle. So when we talk about designing, what we design is we will find out what is the diameter of the throat and exit of the nozzle. Okay, so basically what we found is we found throat diameter and exit diameter of the nozzle in this uh, problem. Okay, so
Okay, sir.
how did we do that is we know what is thrust, we know how much thrust we need to produce, and the
Okay.
thrust is nothing but m dot into exit velocity, right?
Fluoride to no. Okay, sir.
So we know jet velocity. We can find jet velocity based on uh, chamber temperature, chamber pressure, right? Chamber pressure,
Okay.
chamber temperature, and molecular weight, right? All these things are given.
Okay, sir.
Based on
Okay,
that,
sir.
you can find the jet velocity. Once you found the jet velocity, you can find mass flow rate. How much mass flow rate I need to have inside a CD nozzle? Okay,
Okay.
so once you know the mass flow rate, this is the mass flow rate which has to be uh, which should flow inside the nozzle. So if you know the mass flow rate in the nozzle, what we know is mass flow rate is rho AV, right?
Okay.
Rho AV, and it is not going to change. Mass flow rate is here we are considering steady flow isentropic. Uh, in fact, here it is steady flow. So the flow rate at throat and the flow rate at exit is going to be same only, right? Because mass cannot be uh, generated, or I mean mass cannot be distracted or produced, right? So mass
Okay,
flow
sir.
rate at the throat and exit, so we have this relation in this. With this relation, if you go back to the lectures, we would end up uh, uh, deriving this relation based on the chamber pressure and
Oh,
throat area.
throat.
So using this, since we already found the mass flow rate, we can find the throat area.
Okay,
So
sir.
we can find the throat area. Once we found the throat area, we found the diameter of the throat. Okay. So now we
Okay.
have diameter of the throat, and now we can find the exit diameter by having another relation, which is the
Area ratio.
expansion ratio, area ratio. Exactly.
Oh, okay.
So using this
Using.
using this, we found area of the exit, and based
Okay,
on
sir.
area of the exit, we found the diameter of the exit. So basically,
Okay.
you designed a nozzle, design in the sense diameter of the throat and exit. You found out this should be my diameter of the throat and exit, in order to
Okay.
achieve this much thrust. In order to achieve how much thrust? Some 5 kilonewton thrust,
Right.
provided I have combustion chamber pressure and temperature. So that is what we did in the first question. Is it
Okay,
clear,
sir.
Satish?
Altitude. Clear, sir. Altitude is not taken, sir. Can you please explain?
Altitude. Yeah. See, altitude. Yeah, good question. So what we did here was, in the jet velocity, we have this exit pressure, right? Exit
Okay.
pressure of the nozzle. We don't know the exit pressure of the nozzle. This is the
Okay.
exit pressure of the nozzle. But what we are going to design is, we want to design for a optimum thrust, which means the nozzle is going to expand it to the ambient pressure. Okay, right?
Equal to ambient.
Yeah. So PE is equal to ambient. So how do you
And
find the ambient pressure? Ambient pressure. So you want to uh, design it for altitude of 25 kilometers, right?
okay.
At 25 kilometers, what is your ambient pressure? Okay, so that ambient pressure is also given. So altitude,
Oh,
information comes in via
okay.
this.
Okay.
Okay, so altitude, at this altitude I have ambient pressure to be this, so my nozzle should be designed to expand till that pressure.
Oh,
So at this altitude I have 2610 pascals, so I will design my nozzle such that it expands to 2610 megapascal.
okay. Okay. Thank you, sir.
Sure. Anyone else has any doubts? Mohammed, you have any doubts? Okay. Iram, Aishwarya, do you guys have any doubts?
No, sir, I'm clear.
Thank you, Mohammed. Okay. All right. If you, yes, Iram, please go ahead.
Nothing, sir. I
Thank
have
you.
no doubts.
Thank you. Thank you. Uh, Aishwarya, Padmavati.
No doubt, sir.
Okay. Thank you. Uh, okay. If no one has any doubts, maybe I will close this session here. Um, I will upload this session also in YouTube. You can revisit it, and I will upload this PDF also in Drive. I hope that both are accessible for you. If not, please write an email, or it is available in the NPTEL portal. You can explore it. Okay. Well, thank you, everyone. Thank you for attending.
Good night, Satya.
Thank you.